we discussed about numericals regarding our free undamped single degree of freedom motions, and in this session we'll be continuing with some more numericals. Basically we are dealing with free undamped vibrations. Free, that means there is no external amount of load continuously acting on a body which is in motion, or you can say a dynamic force. And undamped, that means there is no dashpot or damper connected to the bodies that we are dealing with. So we have seen 3 sums until now in the previous session. We will be seeing furthermore sums today, having different methodology that we used to see in the last session. So we'll be starting with our first sum of today. The question here is, calculate natural frequency in side sway for the frame that is shown in the figure. EI of the frame is given as 30 into 10 raised to 12 Newton into mm square. It is also been asked, also calculate natural period of vibration, that means time period. This was our first question. In the second part of the question, it is been asked as, if the initial displacement is 25 mm and the initial velocity is 25 mm per second, what is the amplitude and displacement at t equal to 1 second? This second part, or you can say the second part of our question, we have not seen in the last session. This is something new regarding our question that is been asked. So we'll be solving it into 2 halves. First half will be finding the natural frequency, that is small f, and the natural period of vibration, that means our time period. So small f and our time period t will be our part 1. And in the second part, we'll be finding the amplitude and displacement. For that, which data are being given and how to process ahead, we'll be seeing that. But first of all, it has been asked that it is a side sway which is given in the figure. So as we can see here, it is a portal frame, and we need to find frequency in side sway. That means there is a horizontal displacement on this axis. Clear? So as you can see, column AB is of 1 meter and column CD is of 0.8 meter, as you can see here. And there is a weight acting on the beam, that is 30 into 10 raised to 6 is being given in the question. So first of all, we need to find frequency, and the frequency equation is 1 by 2 pi under root k by m. So the first thing will be to find our 2 cases, that is to find k, that is stiffness, and mass. First we will be converting the EI. EI is given in the question as 30 into 10 raised to 12 Newton into mm square. We always need our answer to be in Newton and meter for this case. So here, converting into meter square, it comes out to be 10 raised to minus 6, and the final answer here comes out to be 30 into 10 raised to 6 Newton into meter square. Now mass can be calculated by this equation, that is W equal to mg, so m equal to W by g. Weight is given in the question to be 30 into 10 raised to 6, and g will be our acceleration due to gravity, which we will be taking as 9.81. So this answer here comes out to be 3.058 into 10 raised to 6 kg. So we have calculated the first portion, that was mass. Now we will be focusing on calculating the stiffness. And stiffness depends upon the end condition. So as we can see here, that support A is fixed condition and support D is again fixed condition. We need to find frequency against side sway. So first you need to remember the basic fundas that you discussed, or that you saw in your previous semesters during your SA1, SA2 stuff, that here you can see that if we apply a horizontal load, then the beam will displace. Then what amount or what element which will actually deflect? Clear? So there will be columns which will be getting the deflection. AB column will be getting deflection delta in this case, and CD will be getting delta in this case. Clear? So we will be focusing only on columns if we are finding the stiffness parameters. So to find stiffness, that is to find K, we need to focus on our columns. So as we can see here, that KE, that is our effective stiffness, will be equal to K of AB and plus K of CD. Why plus? Because as we can see here, this is the lump mass model. If we take here as mass, this is a ground surface, then this will be acting as a stiffness material, or you can say spring element, and this spring element is parallel to each other. So for series connection, we saw how to use that equation in the previous sessions, and for parallel connections too. So whenever the parallel connections are given, we always add this portion, that is add the stiffnesses of the individual members. So total effective KE will be equal to KAB plus K CD in this class. KAB will be defined by this parameter, that is 12 EI by L cube. As the end condition is fixed, so it will be, the stiffness equation will be 12 EI by L cube for AB. D is also fixed, so it will be 12 EI by L cube for CD. EI we have already calculated it. Length is given as 1 meter, and for CD length is given as 0.8 meters. So here the final KE comes out to be 1.063 into 10 raised to 9 Newton per meter. So mass and stiffness has been calculated. Now we'll be moving on to our next part, that is our frequency F. For that we'll be finding natural angular frequency. So natural angular frequency, that will be omega, and the equation for omega is omega equal to under root KE by M. K we have already calculated, mass also we have calculated it, so this will be our omega, that will come out to be 18.645 radian per second. Now after finding this omega, we will be focusing on our natural frequency, that means small f. So small f, here the equation will be 1 upon 2 pi under root Ke by m. And as we all know that this part is omega, so we have already calculated omega to be 18.645, and solving it we are getting an answer 2.967 cycles per second or hertz. This is our natural frequency that was asked in our question. It is also asked calculate natural period of vibration, that means we need to find time period, and the equation for time period is T equal to 1 upon F. F we have already calculated, it comes out to be 2.967. So here time period comes out to be 0.337 seconds. So here our part 1 is completed, which we have already seen in the previous session too. Now we'll be focusing on our second part, and for second part it is asked that we need to find the amplitude and displacement. For that the system is idealized as a spring mass model, and the equation for that is given by this. We already derived this equation in the derivation portion for free undamped motion. Clear? So this was our final displacement equation for free undamped motion. We will be using that equation, that is x will be our total displacement equal to x0 will be our initial displacement cos omega t plus x0 dot upon omega. X0 dot will be our initial velocity, sin omega t, omega will be our angular frequency. So here initial displacement is given in the question to be 25 mm, and initial velocity is given in the question as 25 mm per second. So x0 and x0 dot is already given in the question. The remaining part is t. So t, it is already again given in the question that what is the amplitude and displacement, that t equal to 1 second. So the value of t is given in the question to be 1 second. So the only remaining part here is omega. And we have already calculated omega priorly, that omega value was coming out to be 18.645 radian per second. Clear? So this will be our amplitude equation. Amplitude equation again we had derived earlier, is the equation for that will be a equal to under root x0 square plus x0 dot upon omega whole square. Clear? So substituting everything, we are getting the amplitude value to be 25.04 mm. Amplitude is always denoted in mm. Clear? So this is the value of amplitude. The calculation of amplitude is completed. Now we will be focusing on displacement. That means we will be using this equation. So again solving it, again every parameter has been prescribed. After t equal to 1 second, the value of x, that is displacement, will be 24.20 mm. Clear? But most of the students make this mistake while calculating it in your calculators. You always need to remember one thing while solving any parameter pertaining to degrees, that is this trigonometric functions such as sine, cos, tan, etc. You always need to find the values of cos omega t and sine omega t in this equation using the radian mode of your calculator. Do not forget that. While you are using your calculators, always put your radian mode on, and keep in mind that the degree mode is not been on. Always you need to solve this equation using the radian mode. Whenever you are solving this equation using the radian mode, then only you will be getting this final answer, that is 24.20 mm. This is the most important thing you need to do. Because if you fail to do so, then though your entire methodology, your entire equations, formulas will be correct, still your final answer will be having a huge variation in it. Clear? So it will be not getting the full marks that we are supposed to get. So this is the important thing that you need to remember. Now moving on to our second sum of today. The question here is, consider a rigid frame that is shown in the figure having infinitely rigid girder, that is EI for beam is infinity, which is disturbed by the initial condition of x0 equal to 0 and x0 dot, that is initial displacement is 0 and initial velocity is 3 meter per second and the time period is 0. Clear? So we need to find three cases. The first thing we need to find is natural period and frequency, that is f and t. Second, we need to find displacement and velocity at time t. In the previous case, it was asked to be found out at time t equal to 1. Here we need to find at time t equal to t. And the third, that is a new portion in here, is we need to find the forces in columns AB and CD at t equal to 2 seconds. This is something new that we will be discussing later on. The inertia of the columns is being given as 6938 centimeter raised to 4 and the E, that is our modulus of velocity, is given as 20684 Newton per centimeter square. And here is the beam that is being given in the question, that the column AB is of fixed condition having 3 meter length. BC is the beam of 6 meter long having a load, or you can say UDL, of 37 kg per meter. And support D is hinge support and the length of column CD is 3.65 meter. This is the figure that is been prescribed in our question. So the first and foremost thing will be to find the value of F and T. For F, we will be requiring two parameters, that is mass and stiffness. So first of all, we will be calculating mass. As we can see, it is given as kg per meter. So we need to multiply the total span to get the final equation in the form of our mass. So final mass here will be 222 kg. Now we'll be focusing on our EI, because we need to substitute the value of EI in the different parameters. So I is already given in the question as 6938 centimeter raised to 4 and E is given in the question to be 20684 Newton per centimeter square. So multiplying it, we are getting an answer of in the form of kilonewton into centimeter square. But we always need to get our final answer in the form of Newton into meter square. So this 10 raised to 3 is for converting kilonewton to Newton, and this 10 raised to minus 4 is to convert centimeter square to meter square. Clear? So this is our final answer, that is 14.35 into 10 raised to 6 Newton into meter square. Now we'll be focusing on our EI value. For column AB, support A is fixed, so the stiffness of AB will be 12 EI by L cube. Again, column AB and CD are parallel, so the effective stiffness, that is KE, will be, or equivalent stiffness will be summation of both columns. And as we can see, the support D here is hinge, so the equation for stiffness here will be 3 EI by L cube. So substituting everything, we are getting an answer 7263086 Newton per meter. That is our equivalent stiffness. Now after finding mass and equivalent stiffness, the next thing will be to find natural angular frequency, that is omega. So omega in this case comes out to be 180.87 radian per second. After finding omega, we will be focusing on finding our natural frequency, that is F. So F here comes out to be 28.78 cycles per second, or you can say hertz. So our first part is completed, that is find natural frequency. Now we will be moving on to this portion, that is find natural period, that is our time period. So time period here will be capital T equal to 1 upon F. F we have already calculated it to be 28.78. So our time period here comes out to be 0.0347 seconds. So this is our time period. So our part A is completed. Now we will be moving on to part B, that is to find displacement and velocity at time t equal to t. So for that, we have been given initial conditions that the t equal to 0, x0 equal to 0 and x dot equal to 3 meter per second. So here the displacement equation, as we can see here, that x equal to x0 cos omega t plus x0 dot upon omega sin omega t. This was our displacement equation. But we also need to find velocity here. Clear? So to find velocity, we need to find the derivative of this stuff. So the derivative of this stuff will be x dot. Clear? That will be our velocity. So the x dot will be equal to dx by dt. This was our x. So we will be differentiating this with respect to t. So differentiating it, we are getting minus x0 sin omega t into omega plus x0 dot upon omega cos omega t into omega. So this is the value of velocity, or the equation for velocity that we will be using it. For displacement we will be using this equation, and for velocity we'll be using this equation. If it was asked acceleration, then we could have done second derivative of this, and then we could have used that equation if it was asked to finding the acceleration of this stuff. Clear? So first we'll be moving on to this stuff, that is to find displacement. So displacement here, x0 is given in the equation to be 0. So cos omega t, here we can say that we have substituted everything. So here the final value here comes out to be this, that is 0 plus 3 upon 180.87 sine omega, that is 180.87 into t. Now we can't proceed ahead because the t here we need to substitute it in the form of t itself. It is not been asked that we need to find the value at t equal to 1 second or t equal to something seconds. We need to find the value at t equal to t seconds. So this will be our final answer in the form of equation. Clear? So this is our final displacement. Now we'll be moving on to velocity. Again, for velocity we'll be getting some equation based answer. So here we are getting this, that is 0 plus 3 upon 180.87 cos omega, that is 180.87 to t into omega. Clear? So this is the stuff that we are getting for velocity. So our part B is completed. Now we'll be focusing on part C, that is forces in columns A, B and C, D at t equal to 2 seconds. So for forces in columns we need to first know the equation of that, and as we all know that force is equal to stiffness into displacement, that is force is always equal to k into delta. You need to remember this, force is always equal to k into delta. K will be our stiffness and delta will be our displacement. So first and foremost thing will be to find the displacement. So for displacement, in the equation C that we have seen earlier, where we will be putting t equal to 2 seconds in the equation for x that we saw in the answer number B, we got something, or we found out the value in the terms of t. In that equation we will be substituting now t equal to 2, and we will be getting this value, that is displacement equal to minus 7.31 into 10 raised to minus 3 meters. Clear? In this equation that we saw earlier, this was the equation. We will be getting this displacement value after substituting t here to be 2 seconds. Now we will be focusing on stiffness. As we are moving on to this column, that is column AB, the value of stiffness here will be 12 EI by L cube. So here the stiffness comes out to be 6.37 into 10 raised to 6 Newton per meter. Now we have obtained this stiffness and we have also obtained this displacement. So we can find this force, that is our action. So here the force can be calculated through this equation. The answer here comes out to be minus 46.56 kilonewton. Negative sign just indicates the direction. There is no need to worry if the sign comes out to be negative or positive. Clear? So here the force value comes out to be 46.56 kilonewton in negative x-axis. That means, clear? So this was our force in column AB. Now we will be finding force in column CD. So to find the force in column CD, again we will be using the same equation, that is force will be equal to stiffness into displacement. Now as both columns will be displacing at the same rate, the D value is not to be found out again. The D value will be the same that we have found it earlier, that is minus 7.31 into 10 raised to minus 3. So the only thing that will be changing is the stiffness. Why so? There are two basic reasons. First, the length of the column is being changed, and the end condition is also changed. Clear? If the length and end conditions both would have been same, then again there is no need to find the value of stiffness too. Clear? But here we'll be finding the value of stiffness. So stiffness here will be using the equation 3EI by L cube, and that comes out to be 885308 Newton per meter. So again solving the force equation, that is A equal to S into D, the final force that we are getting is minus 6.47 kilonewton. That means 6.47 kilonewton in the negative x-axis. So this is the force in column CD. So our three cases that were asked are completed here. Now we'll be moving on to our final sum of today, that is find the natural frequency of the system shown in figure. This is the system that is being asked in the question. It is also been asked in your GD examination too, that there is a mass of 50 kg being connected through a rough surface, as you can see, through various types of springs, so various amounts of spring. So here we will be getting to know the basic fundas of series connection and parallel connection, and we will be finding the natural frequency, that is F. Clear? So first and foremost we will be calculating the KE. So there are 4 springs connected, so we need to find equivalency of all 4 springs, but we will go in step by step manner. First we will be taking these 2 springs, that is K1 and K2, and as we can see that K1 and K2 are in parallel here. So springs K1 and K2 are in parallel, so KE1, that is equivalency 1 between K1 and K2, can be solved as K1 plus K2. This, that is K stiffness for K1, K2, K3 is given as 5 Newton per mm, and K4 stiffness is given as 10 Newton per mm. So here it will be 5 plus 5, that is 10. Now these 2 springs are being combined in the form of KE1. So now this will be our KE1, which will be in series with KE3. Clear? You can get it. This will be our KE1 combined, and this will be our K3. So KE1 is now in series with K3. So for series connection we already know the equation. So now we will be getting the KE2, that is KE, that is equivalency of stiffness in the part 2, that is we will be dealing with all the 3 springs. So KE1 into KE3 divided by KE1 plus K3 will be our equation for the connection in series connection. So 10 into 5 upon 10 plus 5 will be giving our answer, that is 3.33 Newton per mm. So we have proved equivalency of all these 3 springs. Now we will be getting the equivalency between these 3 springs and this K4. So this spring which we have equivalented, so this will be one spring now, and here will be other spring. So these both are again in parallel. Why parallel? Because there is a mass in between. So whenever there is a mass in between, both these springs are to be considered to be in parallel. Clear? So now springs K2 and K4 are in parallel. So the final K, that will be KE3, will be equal to KE2 plus K4. So our final answer comes out to be 13.33 into 10 raised to 3 Newton per meter. This is the total equivalent stiffness of our entire spring mass model. And the ultimate goal will be to find the value of frequency. The frequency here will be 1 upon 2 pi under root K by M. K will be substituted in the final equivalency, and we are getting an answer 2.598 cycles per second, or you can say hertz. But keep in mind, if it is not asked to find time period, we always will be finding time period even if it is not asked. Clear? So time period here in this case will be T equal to 1 by F, that is 1 upon 2.598, that comes out to be 0.384 seconds. So this was our basic sums pertaining to free undamped motion, and this will be our today's exercise problem. Do solve it, because it is generally asked in your GT examination regarding these problems. Clear? So this will be our numerical part. In the next session we'll be seeing another derivation stuff of it.